All right, let's start the lecture. I will first review what we are doing. All right, let me start the lecture, helicopter one. Don't worry about homework, I will collect at the end of the lecture. So we were working on proving helicopter one theorem. You remember you have to prove two implications. Causal implies that G of n is 0 for n negative, and vice versa. We proved the backward implication last time. Now we want to prove the forward implication. But to prove the forward implication, I will not prove directly, but the goal is to prove the contrapositive. So we assume that this is not true, G of n equals 0 for all n negative, and we want to show that S is not causal. But last time we couldn't figure out which of those is correct. So I imagine that you had time to think about this. So let's vote again and see if there's some progress. All right? So which one is equivalent to not this? How many of you vote for the first one? The first one had the majority last time. And now only one person. Okay, who votes for the second one? The third one? The fourth one? The last one? Wait. I expect you to get more mature about it, and then you get less mature. All right, so it doesn't help to wait. All right. So another way to deal with this is that you answer the question I asked you in class. I'm going to make a statement, and I want you to formulate the exact opposite to my statement. My statement is all students on my left side have a black notebook. What is the opposite statement to this?
One student does not have black notebook?
On my left side or the right side?
On this side, on your left side. You say that all of them have it, at least one doesn't have it. Or at least one does have it, not all.
That is ambiguous because I don't know if you mean that every of those students don't have a black notebook.
All students on the left side have a red notebook.
Right, so you mean by this that every of them don't have a black notebook. That's what you mean?
No, you said every student on the left side has a red
I want to understand exactly what you mean.
What color of notebook is it the left side has?
You restate what you state.
All students on the left side doesn't have a red notebook.
So does it mean every of those students don't have a black notebook?
Yes.
Okay, wrong. This is wrong.
At least one student doesn't have a red notebook.
On the right side?
On your side, I don't care.
What I said is that every student on my left side has a black notebook.
At least one student on your left side doesn't have a red notebook. One student on the right side doesn't have a black notebook.
This is wrong. This is correct. This is correct.
So if all students on your left hand side have black notebook, then it means that the opposite is on the right side. So all students on the right side.
Wrong. 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 Correct. Wrong.
Also, in the left side does have
Right? Right?
also in the left side does have a black.
You're just repeating what you said. All of the students on the left side that doesn't have a black notebook. Oh, okay. All right. So I'm going to say, I repeat, my statement is that all students on my left side have a black notebook. The majority of you said all students on my left side doesn't have a black notebook. This is wrong. That's not the opposite of my statement. That's wrong too. All right, so the correct answer is what you said, and what you said is that at least one student on my left side doesn't have a notebook. This is exact opposite. Exact opposite, it means the exact opposite is the exact argument that is going to contradict me. This is the exact opposite, because it could be your statement is not the exact opposite, because it could be that your statement may not be realized, and yet I could be wrong also. What I mean is that your statement is not the exact opposite because your statement could be wrong and my statement could be wrong at the same time. So they are not exact opposite. If they are exact opposite, if this is wrong, the other one must be true. All right, after we have done this exercise, now we vote here. Again, how many of you vote for the first one? How many of you vote for the second one? How many of you vote for the next one? How many of you vote for the next one? And the last one? Oh, sorry. Now, it cannot be for the bottom. You cannot say for all at least. The last one. The last one. 0. Of course, it's this one. You know, I find amazing that, okay, you may complain that this class is difficult in math, for example, but this is not about math. It's pure logic. So, is that why this class is difficult? Because it's pure logic? Is because you are not logical? That's the reason? Okay, this class is hard because you are not logical. What can I do? All right, so be logical, and then you'll be good in this class. All right, so another way to state this is to say there exists I'm going to say n1 negative such that g of n1 is non-zero. That's the exact opposite. Right? So we're going to assume this, and we're going to prove that S is not causal. Now, previously we showed that we have this formula. Okay, so we know we have this formula because the system is RTI, so the output is obtained by convolution. So let me rewrite this. All right. Now, we know that when you do this summation, one of these terms corresponds to k equals n1, right? So in this expansion, one of them corresponds to n1. You agree? One of them, one of these terms is this one. So since g of n1 is not zero by assumption, then y of n naught depends on x of n naught minus n1. You agree with that? All right? The question now is n naught minus n1, is it the past or the future of n naught? Is it past or future of n naught? Okay, let's vote. How many of you vote this is the past? How many of you vote this is the future? Oh, you see. And one is negative. So this is the future. This is greater than n naught. So this is future. So S not causal. Done. I'm done with the proof. So let's return to the theorem. The theorem says that when the system is LTI, you just need to look at the impulse response, which we call G of n, to check whether the system is causal or not. And the test is that it's going to be causal if and only if G of n is 0 for all n negative. But if there's one element that is non-zero for n negative, then the system is not causal. And we saw an example with the previous example I gave, right? So why did I call this theorem helicopter? All right, I'm going to tell you. Normally, if the system is not LTI, if I ask you if it's causal, you have to look at the formula, and you will have to look manually if the output depends on the future of the input, right? But if the system happens to be LTI, you no longer need to do that. You just need to you just need to inspect the impulse response. It's a shortcut. It's a shortcut. All right, so normally I like to teach in a classroom with a window. But imagine there's a window, and after the class you return home. You live in, I don't know, Queens. It takes 1 hour and a half for you to return. But suppose there happens to be a helicopter showing up and saying, hey, I can give you a ride or a flight, I don't know how you say. I can fly you home in 5 minutes. Will you reject that? Okay, so we are in an ideal world where there's no accident. But in fact, at exams you have so many accidents anyway. So will you reject that? You can, but you know, in the exam, you want to do things as fast as possible to get the maximum number of points, right? So no, you don't want to miss that helicopter if it presents itself to you, right? So what happens is that quite often you don't realize there's a helicopter because you don't realize that the system that is given to you is LTI. So you suffer looking into a formula. But what happens is that I have been so good at making you think in terms of helicopter that some of you end up taking helicopter when there is none. Let me tell you, suppose that, when I teach at Mac building on the 4th floor, you jump out of the window without helicopter, you know what happens? It hurts, right? And that's what I write in the exam, you know? No helicopter, it hurts, and then there's a 0 below, right? It does hurt, right? So what happens is that when I was not teaching so well, people just would forget about helicopter, but now the new trend is that too many people take a helicopter when there's no helicopter, so that is create very funny situations, not for you, but for me. All right. So what happens is that we are going to now go to the next property, which is stability. And stability will also have a helicopter version, which will be called helicopter 2. And because of that, some students, they always want to take helicopter every time, but all right. So it's what, 9, right? So this is the hardest property among the 4 properties. Because to understand a stable system, you need to understand first something intermediate, which is called bounded sequence. So that is something that students sometimes don't understand. A sequence x of n is bounded when there exists a constant A such that for all n absolute value or magnitude of x of n is less than A in absolute value or in magnitude. That's the definition. Is it easy to understand? No, a constant is a single number. All right, so you see the opposition constant here, but this has to work for all n. All right? All right, so this is a valid definition for complex sequence, but when x of n is real, you know that writing that is equivalent to saying that x of n is between minus A and A. All right? You know that is the same thing. So when you plot your sequence, so x of n, so x of n x of n is less than A for all n if and only if you get this picture. So you plot the sequence. Okay, I don't have time to show all the bullets, but here I plot the value plus A, and here I plot the value minus A. So for the sequence to be bounded by A, when you plot it, you must see plus A as the ceiling and minus A is the floor. So if I say ceiling floor, is it easier to understand? All right. So now you understand what that means, bounded? All right. So let's see. Example. All right, I consider the sequence x of n equals n. And you're going to vote. Are you ready? Yes. How many of you vote this is a bounded sequence? How many of you vote this is not a bounded sequence? Like that? I always like to do that. But okay, those who said not bounded, can you tell them why it's not bounded? Okay, actually, if you plot this sequence, are you able to find a ceiling? Are you able to find a ceiling?
No, that would be n.
Done. Done. That's as simple as that. Or okay, actually, very easy. Imagine a house where the staircase never stops. Can you put a ceiling on it? that's easy, yeah. All right. But I know those who said bounded, I know why you said. It's because n is finite. Well, I don't really care. Because imagine you have a staircase that never stops. Each step is finite. Each step is finite. But there's no way you can bound this finite value. You know, I have fun going to work when I can have fun with the students, like that. Ready to vote? All right, how many of you vote this is bounded? How many of you vote this is not bounded? Wow, it's a bit tight. All right, those who say it's bounded, why do you claim that? All right, that's a good point. I'm not saying this is the final answer, but it is true if you take the limit. You get 1, right? Fine, that means when you are far enough, you cannot be big or small, right? You cannot be big, okay? Right, when you are far enough. When you are far enough. What about in between? Did you get the issue? So we understand when n is large enough, we are not going to have trouble, right? Because it's going to be close to 1, so it cannot go crazy. Yeah, but what about in between when n is? Huh? Why is that? Okay. All right, I give you the answer. I give you the answer. I give you the answer. If the function was continuous time, your reasoning wouldn't work. It can be bounded infinitely, but it can be unbounded in between. It's possible. But here we are in discrete time. That means, let's say when you are far enough, you know you're not in trouble, right? So let's say when n is larger than 1 million, you are fine. But between plus 1 million and minus 1 million, you still have like 2 million numbers. You know what? Among 2 million numbers, there's always one that is the greatest one. Always. Always. Because 2 million is a finite number. It's like on Earth, there is a man or a woman who is the tallest. It exists. She exists, right? I don't know where. I think it's somebody in Turkey, I think. But right? But even though we don't know where, we know he exists. Isn't that amazing? It's like one of these absolute thinking of math, right? So that's the reason, yes, it's bounded. Yes? So when it's continuous, it could be, for example, that you get a function like that. You see, when it goes to infinity, it goes to 0, but in between, it can blow up. You see?
So Professor, I would say that if we have a limit number, then it will be bounded.
Yes, you can claim that. You can claim. All right, so okay, now I'm going to give you a third example. All right, so I want to warn you in advance. If you don't understand it, don't worry. I'm adding this example because I just wanted to have fun for myself. All right, so just for fun. All right, so entertainment, 5 minutes. So don't worry, I I say for fun, all right? Once in a while, the teacher wants to have fun. That means I will give you the answer. You may not understand it, but it's all right. It's all right. Just all right. How many of you vote this is bounded? How many of you vote this is not bounded? All right, so we have a, you know, when you invert something, the issue is that when this value is 0, right? Can cosine of n be equal to 0? No. Right. All right. Okay. Okay, it's fine. I give you a second chance. Let's vote again. So how many of you vote this is bounded? I put the old numbers. And how many of you this is vote this is not bounded? You want to, you insist? Anybody wants to take a chance, like with him? You?
Are you blocking or are you double vote?
Triple. 3. Yeah, anybody wants to take a chance? Yeah? Yeah, you want to take a chance? Okay.
No.
But the guy behind, yeah. Should I continue or should we continue? Should we continue the massacre? All right. Answer? You did right. Actually, it was like a game, right? Like when playing poker. Okay. All right. Cosine of n can never be 0. That's true. However, there is a however. It is always possible to choose n so that cosine of n is arbitrarily close to 0. You understand what that means? That means you give me a number, any number, it is always possible to find an n that makes cosine of n less than the number you give. Now, n is always an integer. But you give me a number, as small as it might be, it is always possible to find an n if you choose n large enough to make it cosine of n close enough.
For this example, you can't find the 0, you just cannot find the floor. For this example.
Here, I cannot find the floor of cosine of n, therefore I cannot find the ceiling of the inverse. All right? Okay. I repeat, it was for fun, all right? So if you don't understand this, don't worry. If you really want to understand this, then you should apply for graduate math department, all right? Or you come to my office, all right? Because it's a theory of irrationality and all this, which is fun, but it's hard. All right. So now, I assume you are very well trained for bounded sequences. So now we're going to talk about stable systems. Okay, so I'm going to give you a definition, and let me tell you, many students don't understand it, even though the statement will be very simple. a system S is stable when every bounded input gives a bounded output. When you see the statement, it looks like, whoa, what's the big deal, right? It's very easy to understand. Let me tell you, sometimes you think you understand it, but you don't understand it. So, I repeat, a system is stable where every bounded input, which means every input that is bounded, okay, I'm just repeating myself, is guaranteed to give an output that is bounded. We know what means a bounded sequence, right? We know that. So, S is going to be stable when every time you input a sequence that is bounded, you are guaranteed that the output is going to be bounded. I'm just translating what is written, but I'm just saying the same thing.
How can we know?
How come we know the input is bounded? That's
No, all the input. Because we cannot input all of them. Or
you should try. That's the point. No. Here, no. But here we're not going to talk about impulse response because here we're not dealing with LTI systems. Remember, if the system is not LTI, impulse response is of no use, no help. All right. But remember, for time invariance. For time invariance, you want to make sure that every shift of the input is going to give you the same shift of the output, right? So don't ask me, do we have to look at every shift? Because you did it, right? You did it. I mean, to prove it's time invariant, you did put every possible input shift, right? You call it n naught, but you didn't specify the value of n naught, so that means you try every, right? So same thing here. All right. Now, a typical confusion that I hear is that I prove that something is stable by inputting something that is bounded, and then often I hear the questions, Professor, but then what happens if you input something not bounded? Exactly. Exactly. Exactly what you said. I don't care. You can do it if you want. Yeah, do it. I don't care. Right? So, you understand that, right? Because some students get confused is that, all right, you input something bounded, but what if you input something not bounded? And I say, okay, it's your problem. It's not mine. All right, so ready for the challenge? Yes?
so we need to prove that it's bounded for n naught.
And not?
That the input is bounded for n naught.
And not?
For
The-
any
There's no and not here.
for every input.
Yes.
We need to show that.
Yes, you do it. You do need. Yes, you do need. Right. So you kind of see why I said it's the hardest property, right? All right, ready for the challenge? We're going to have fun. All right, so again, a system is going to be stable or not stable. There's not going to be anything in between. It's going to be yes or no. Is that a question or a vote? it doesn't say that.
I'm asking.
The answer is that the statement doesn't say that. That's the answer. That's the answer. All right? All right. Are you ready to vote? Okay, how many of you vote this is stable? How many of you vote this is not stable? You got trapped by your question. Actually, the question, the answer was that we don't care about the value of the bound because it's not stated in the statement. All right, so those who voted no, they got tricked. They got tricked by the idea that probably the definition implied that the bound must be the same. But it doesn't imply that it must be the same. It could be that the bound of the input is 1 and the bound of the output is 1 trillion. We don't care, it's stable. Yes?
When you give us a statement like that, I mean, are you telling us that the input is bounded?
No. No, I give you a system. I give you a system. It's for you to do what is necessary to do to state whether it's stable or not. Right? I don't give you any input, I give you a system. All right, I'm going to prove it for you. All right? I'm going to give you the formal proof. Yes? All right, wait. I'm going to prove it to you, okay? I'm going to show you the proof. All right? Proof. So to prove that the system is stable, you must consider an input that is bounded. Right? Because don't consider an input that is not bounded because I'm going to say, and you're going to say, I don't care. So take any input, any given input x of n that is bounded. All right, so I take one of them. But since we assume it's bounded, then we know then there exists a such that x of n less than a in absolute value for all n. All right? Because we agree. No problem. Now y of n is what? So y of n, which is s of x of n is what? Now, do you agree? Do you agree that y of n is less than b with b equals a squared? Do you agree with that? For all n? Right? You agree? So y of n is bounded. Done. Yes?
The stable system is at one. The first stable system where you put one input that is bounded, it gives you a bounded output. But there's another input that is bounded, it gives you essentially another output. This is the first system. No, I'm saying
No, there's no reason. Nobody said that. Nobody said that if you just check one input, it's enough to know the other inputs. There's very little chance that this happens. You know, it's the usual business. If you know the system for one input, there's no reason to know the system for other inputs. You see, S has no property. We don't know anything about this.
Professor, you're assuming that x of n is boundless.
Yeah. So you're going to say, what if the input is not bounded? I said, we don't care. You got trapped.
No, you assume that x of n is bounded.
Yeah. So the question is, what happens if x of n is not bounded? Is that the question? I prepared my gun.
But if we're looking at the first example, we're looking at where it's just x of n equals the first example before.
No. But the examples were about the.
Like, I'm just trying to look at something that's unbounded. So x of n equals n. You know, you get up to a certain point where you achieve finite numbers that are bounded.
You are going to input something that is not bounded, right? You want to take x of n equals n.
Well, but it has values that are bounded.
Wait. No. We don't talk about a value that is bounded. That doesn't make sense. Because the notion of bounded is you have this for all n. There's no notion of bounded value. That does not exist. We say finite value. We don't say bounded value. But it's the term, it's the definition. Okay, don't get mixed up.
So we take a bounded input that we know is bounded. We put it in the system, and it has to give a bounded output.
You're just repeating the definition of stability. I know that stability is creating confusions, but I'm not able to describe what happens in your brain. If I could read, I would say, no, your thinking is really wrong. I read, no, don't think this way. No, I can read already, it's wrong. I told you that the stability is where I have a lot of fun.
And x of n could be any input, right?
You want this to work for every possible boundary input. The class is very noisy today, so stability is creating difficult. Okay, if you get confused with the example 1, then example 2, you will die. Everybody is okay for example 1? Okay, so let's have more fun now. Even more fun. Did you notice I give you more time? It's bad sign. It's a bad sign. All right, let's vote. How many of you vote this is stable? How many of you vote this is not stable?
I'm gonna switch to Wednesday.
Really? Why isn't that stable? Why isn't that stable? Is it allowed?
Yeah.
Is it allowed?
Yeah, it doesn't have to be next year.
Oh yeah, I see what you mean. Yeah, it's fine. You're right. You're right. He got it. The requirement for stability is to test with a bounded input. Is a bounded input allowed to be close to 0? Yes. Yes. That's the answer. There's no problem for a bounded input to be close to 0. But do you see what happens if this happens? It blows up. The output blows up. Right? So, now to disprove that the system is stable, it is sufficient to find one. Okay, you tell me what. I want to disprove that the system is stable. So it is sufficient to find one output that is such that the output is So you complete. Find an input that is such that the output is So an input that is bounded such that the output is unbounded, right? If you say it is sufficient to find an input that is unbounded, you get shot already. Because we don't care, remember? All right, so consider x of n equals one over 1 plus n squared. Is that bounded? Yes, it's less than 1. It's less than 1. When you divide 1 by a number that is larger than 1, you get something less than 1, right? Because x of n less than 1, right? But what is y of n? Do you agree? Is that bounded? Not bounded. So the input is bounded, but the output is not bounded. So S is not stable. All right? Example 3. Okay, example 3 is I forgot. So you know what I'm going to do? I'm going to look at the previous semester. But then you're going to see the answer, right? So I'm going to look into the previous semester. So you close your eyes so that you don't look at the answer. So I look at previous year or previous semester. Lecture. All right, I know you are not going to close your eyes, so I'm going to close your eyes for you. All right, this is great. It doesn't work. It doesn't work. Okay, somebody is interfering. Display status. I see that somebody is. Oh no, it's working. I was wondering what was this. Who is that? Who is that?
What, the admin?
Yeah.
That's the board.
Oh, I thought it was one of you. Like trying to display his own stuff instead of mine. Okay, you will see on the video the answer, but it will be too late. All right, so. Let's vote. How many of you vote this is stable? How many of you vote this is not stable? Why you think it's not stable? Why you think it's stable? Sorry.
Stable because no matter what input you give it, any cube will still be have a ceiling to it. Even though there's that whole weird condition, if we just ignore the condition, for example, and the cube will always have some sort of ceiling to it because it doesn't have a ceiling.
Why is that?
It's just like example one. And then let's say you put in 100, it's just going to be 100 cubes. But if let's say 100 is your max thing, that's your ceiling. That's the cube. So for here, ceiling would be 80.
No. It's not going to be 80. Anybody? All right. It is stable, but the explanation is more complicated. Because n cube can go as high as you want. In example one, x of n couldn't go as high as you want.
So can it also make it all down to
All right, so I'm going to explain to you why. What happens is that this case only happens if n squared is less than x of n. But if x of n is bounded, then x of n will be less than a. So the first case can only happen when n squared is less than a. But n squared less than a means n less than square root of a. So n cubed is less than square root of a to the cube. So it's more complicated. It's much more complicated. All right? All right, so proof. Take x of n bounded. So there exists a positive, non-negative such that x of n less than a in absolute value for all n. All right. So to obtain y of n equals n cubed, we must have n squared less than x of n, which is less than a. So n cubed so y of n cubed less than cubed. All right, so n is less than square root of a. So either y of n is equal to this, so it has to be less than this, or it is 0. So y of n is bounded. So S is stable. Okay, you see that stability is the hardest. All right. So, CRM. So, same idea. Let S be LTI and G of n its impulse response. Then there's a way to check the stability of a LTI system by just looking at the impulse response. But what is the test to be done on the impulse response? So S is stable if and only if. So it's harder. It's harder now. The sum of magnitude of G of n when n goes from minus infinity to plus infinity is finite. That deserves a proof. All right, so the theorem says that to state whether the system is stable or not, you just need to perform the sum of the impulse response in magnitude. If the sum converges, then the system is stable. If it diverges, then the system is not stable. All right, so I'm going to prove that. Okay, so proof. So again, since the system is LTI, we can state right away that we have this. So that's why I I copy it. We have this. By the miracle input theorem, then the output is the convolution between the impulse response and x of n. So y of n, so here we don't care about this. We have y of n equals this in general. All right, so again, we are going to prove two implications. Again, it's easier to prove the converse. So assume that this is finite. And then prove that S is stable. Now, since this is finite, then it gives you a number, right? We call it B. All right? Now, take x of n bounded. So again, take x of n bounded. So take x of n bounded, then there exists A such that this is less than A for all n. All right. Okay, so now we're interested in what? We're interested in magnitude of y of n. All right, so it's going to be the magnitude of the sum. Now, let's do some review. What is the magnitude of A plus B? It's amazing that you don't know the answer. I have always find this amazing. So you remember vectors? So this is like a vector A, vector B, and this is vector A plus B, right? Yeah? Now, you know complex numbers. They are like vectors. So now magnitude of A is the length of the vector. Magnitude of B is the length of the vector. A plus B gives you this vector. Now you want to go from this point to that point. You go like that or you go like that? You go like that. Why? It's shorter. This is shorter than this. Don't tell me you don't know that. Let's see. You know that we have a square. We have a square in front of, I don't know the names of those buildings. You know that you have a square with a round like a fountain? Yeah, the quad. But so you want to go from one corner to the opposite corner. What is faster, take the diagonal or go like a rectangular? All right, so this is the same thing, right? All right, so now we don't have a sum. So this is not sum of A plus B. It's the sum of A plus B plus C plus D, but it's the same thing, right? So I can say this is less than but what is the magnitude of A times B? Wow. You're not good. You don't know that. What can I do? All right, so this is also equal to all right. Now I'm going to write something that is different. Instead of writing x of n minus k, I write a. So is there anything you can say about the comparison between these two numbers? Look, the operation is the same, except that here I multiply by something that is bigger than this. You agree that this is bigger than this? Because we know it. It's true for all n. It's true for all n, so this is true for n minus k. So this is bigger than this. So what do you say about the global result? Isn't that obvious? All right. But now we do a sum, but A no longer depends on K. So what do you do? Yes? You can factor it out, right? But that is what? B. So it's a number B, AB. Y of n is less than AB for all n. So y of n is bounded. So S is stable. All right, I'm going to do a survey. How many of you are scared by this proof? Okay, I'm not able to count. It must be like 30. Wait, you understood every step, right? And yet you are scared by the proof. You understood every detail, but yet you are scared by the proof. I don't understand that. Actually, I understand. Is that you are scared, is that you understand every step, but how did I get the whole idea? All right. So I will say, okay, I will not ask this proof at the midterm exam. In fact, I will not ask any proof at the exams. Is that good news? All right. But you still have the proof. We still have the proof. That means at least you have the guarantee. You know, it's like the golden guarantee of some currency. You have the golden guarantee here, right? You can check that every step is working. All right, we still have to prove the other direction, the other implication. You got scared by this proof. The other one is 100 times scarier. All right, I need more of this. I need more of homework.